Well, hello, my name is Chris Barkin. I want to welcome all of you to the William W. Hay Railroad Engineering Seminar here at the University of Illinois. Before I introduce our speaker, I'd like to take care of a few housekeeping items. First of all, the usual, if you have a cell phone, please put it on mute or turn it off so that it does not disturb the speaker. If we have a fire alarm, what I'd like you to do is in an orderly fashion exit from these two doors and descend the stairs to ground level and then exit the building. And what we'll do is we'll assemble on the north side of Main Street. And I would like to use the buddy system, so pay attention to who's next to you and make sure that that person gets out safely. We're not expecting any severe weather today, but if we were to have severe weather, instead of going down these stairs, we would stay on this floor, walk on the hallway behind this wall into the old part of Newmark Lab, and as soon as you're in the old part of Newmark Lab, go down the stairs to the basement. It's a very safe refuge from any severe weather. We'll be passing around the attendance list. If you did not sign it already, please add your name and affiliation. And if you did not receive a direct email announcement at this seminar but would like to in the future, please include your email address legibly on that form. I'd like to welcome those of you who are joining us via the internet. We have a number of organizations represented: New York State DOT, TTCI, Northwestern University, Railstar Engineering, URS Corporation, Hanson Professional Services, CSX, Oregon State University, Illinois Department of Transportation, University of Wisconsin-Madison, Parsons-Brinkerhoff, Chicago Transit Authority, Parsons, Metra, AECOM, University of British Columbia, Okanagan. I'm getting the nod from the back of the room here. Welcome, Gord. Transport Environmental, Michigan Tech University, and several other organizations. So welcome all of you to today's seminar this afternoon. And by the way, those of you either dialing in or here in person, if you would like to receive continuing education units for your participation, please send an email to LD Fry. Her name and email address is on the seminar announcement. What we want to do is improve the ability of the online audience to hear questions from the audience. And so we'll be using this microphone. If you have a question, just raise your hand and we'll bring the microphone to you. And that way everybody can hear the question. Let's see, do we have a ARIMA student chapter announcement? Okay, well, I believe I did see an email. So as is usually the case, the ARIMA student chapter will be having happy hour. I believe it's at the Blind Pig on Walnut Street at 5:30 this afternoon to continue the discussion of this seminar. The speaker informs me that he's considering, I think facetiously, unfortunately, considering canceling his flight and staying over. But so the William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois in Urbana-Champaign. On behalf of all of us here at the university, we thank the U.S. Department of Transportation for their ongoing support of this seminar series. It's greatly appreciated by us on campus as well as those of you who are participating via the internet. A little bit about the presentation. During the 1990s and through the mid-2000s, the U.S. railroads frequently experienced periods of extended network congestion. Now, while this congestion was not prevalent at all locations at all times, it was still evident in national performance results. And there were several reasons for this, including rapid traffic growth, change in the type of traffic, and a number of major railroad mergers. All these factors compressed into a relatively short time frame resulted in significant disruption of the industry. This presentation will consider the most important factors that created the congestion and the solutions. We have an extremely qualified speaker. We're very pleased to have him here today. John Gray is Senior Vice President, Policy and Economics for the Association of American Railroads. Prior to joining the AAR, he worked for the Union Pacific in business development as Vice President and General Manager, Industrial Products. Before working at UP, he held commercial, operating, and strategic positions at Southern Pacific Railroad, Burlington Northern Railroad, ARCO Alaska, and the Alaska Railroad, as well as a faculty position at the University of Alaska. Prior to that, he held a commission in the U.S. Army and served in Germany for 4 years. Mr. Gray is a member of the Executive Committee of the Transportation Research Board and a member of the Board of Trustees of the John Berringer National Railroad Library. He holds both bachelor's and master's degrees in civil engineering from Tulane University and did postgraduate work in mathematical modeling of transportation networks and rail cost analysis at Northwestern University. Please join me in welcoming our speaker today, Mr. John Gray, who will present the William W. Hay Railroad Engineering Seminar on Measuring Performance of the National Rail Network.
Thanks, Chris. Sounds like the mic's on, so we kind of go forward on it. First of all, I've had a chance the last couple of days here to spend some time with a number of folks that are doing some work in various areas. A lot of it related to things that we were going to talk about today, and quite frankly, you've set a pretty high standard. It kind of worries me on trying to get the information here, because the standard of work that I've heard and I've been exposed to is really, really nice. It's nice to see the work going on. It's nice to see work of this quality being done about the rail industry. But as Chris said, the area that I'm looking to talk to is this whole area of what happened back in the mid to late 90s and the early part of the last decade in the rail industry, because I think it has some fundamental lessons on some of the things that are important in management going forward. And what I'm going to do is talk about this in terms of data that is publicly available, and that's one of the big items that we're looking at when we put this together. Was we wanted to be able to use data that was publicly available, not have to do things that might or might not violate confidentiality agreements with various parties. And so what we're using is some publicly available data to look at whether you can see what some of the critical issues were back then that really caused some of the big problems. And again, as I say, the conclusions out of that I think are important, because they get to some of the real important areas for management, for research, and for a lot of things that I see going on here, looking into the future. Let's say the project that we worked on, it was back in April through June of 2011, was to examine the period from 1987 to 2009 and look at some of the performance metrics that came out of that time, where you could with publicly available data. The project was sponsored by TTCI, and it was initially designed to look at the impact of congestion and disruption in the network on the cost of things such as fuel consumption and additional operating costs that came together. I'm not going to talk about that today because it starts to get way too long and involve going out, but I would like to talk about the things that led up to being able to do some work on that. Why this period? Again, it was one of prolonged stress and network reconfiguration. Over this whole period, you saw various activities involving reconfiguration of the network, either through consolidations within the industry or through redesign of the way the network was being operated. At the same time, particularly up through 2006, you had rapid growth in the amount of freight that was on the network. You had a growth in all the areas of freight traffic, of the 3 areas of freight traffic there. You had also a refocusing during this period of the portfolio of business towards intermodal and bulk business. so that you're getting more unit trains, more intermodal business as you went forward. It was also, as I say, the period of the most significant rail restructuring of the last century. More got done in consolidation and restructuring during this 20-year period than you'll see the entire rest of the 20th century. And one of the real reasons for looking at these specific years was that's where we have really good data. You have consistent data during that period. If you look back before 1987, you start to see some discontinuities in the publicly available data that make it really difficult to get time series that's meaningful on a lot of issues. Just to reflect briefly on the amount of freight that was being added to the network. Over on the right, you're looking at the freight addition that were taking place in terms of the number of units, either intermodal units, trailers and containers, or rail cars that were growing. Obviously, the one with the fastest rate of growth was the intermodal business there. Basically train load type business that was the growth engine there. But in terms of units particularly, all the business lines were growing. The bulk was growing faster than the manifest business, also the individual car business. Everything was growing. Same thing you see in tons here. Although when you look at the intermodal tons down here at the bottom, it doesn't look like they're growing because there's just not many of them in each unit. So the units grow much faster comparatively than the tons did in a lot of the other businesses. And in fact, in the manifest business, the tons kind of stayed flat during that period, even though there was a growth in the number of units handled. Strangely enough, in that business, but when you look back at it, you start to understand that the mix of business changed, and there was a lot of growth in the automotive business where you didn't have many tons in the individual. The scope of the analysis, again, we look at it at the national level in this, and although it is possible to take the same formulaic issues and drive them down to individual railroads because of the reports that we have, we don't try to go to individual railroads because what we wanted to see was the impact on the network as a whole. And the reality was that this did have an impact on the network as a whole. It wasn't an individual railroad issue that we were dealing with. Sources of the data on it, annual reports, R1. I don't know how many of you may be familiar with the annual report R1 that the railroads do for the Surface Transportation Board, but there's lots of data in it. It's just a gold mine of data, and it can be made even more robust if you know how to tease the information out of that data, and you work with the data and give it. Takes a lot of love with it, but it can tell you a lot if you're willing to spend the time on it. The other item was the quarterly commodity statistics that is also reported to the STB. Gave some background on some of the business trends there. Now, understand that there's discontinuities and there's conflicts with it, both within these data sources and between them, as well as some of the other data that we need to track down. And obviously we had to resolve some of those. In quite a few cases, we had to resolve things that were in this data. Okay, one of the questions we get when we talk about this project is, first of all, why didn't you use the service metrics that are published on a regular basis? You're looking at service performance. Why don't you use the service metrics? Basic reasons out there now. The service metrics as they exist today that are published on a weekly basis by AAR didn't exist until 1999. They came out of some of the disruptions that happened back then. So they weren't around for the entire period that you needed it. You didn't have any baseline data if you use the service metrics. Two, they're designed to do something different from what we were looking for. They're designed to provide customers current information, not necessarily provide information that is useful when you try to drill down. I think if there was a study done back in 2008 on rail service and rail prices by Christensen Associates up in Madison, Wisconsin. And they tried to use this data for the purposes that we're talking about here, looking at service as a time series. And they discovered, for a lot of the same reasons that we didn't use it, that it's not a useful for looking at the service dimensions very well. So the specifications for some of the individual data elements have changed even over the time since 1999. We've had to learn how to use this stuff. So that if you look back, particularly prior to about 2005, there's been enough change in the data elements so that it's not reliable to try to make comparisons with data before that time. And finally, during this entire period, it's not fully comparable across railroads. So as appealing as some of this data might be to try to understand some of these factors, there's enough problems in it that can't be easily resolved, that it's not something that you want to use. So the hypothesis that we finally came up with in looking at this is that the most probable factor that created a lot of this congestion was the growth in traffic. I know that the traditional thinking on this is basically that it's the consolidations that were the problem, and there were certainly problems that were related to a lot of the consolidations. But we think that the reality was that this problems were started long before the consolidations were there, and that in fact the consolidations may have been the key to solving the problem rather than the final manifestation of the problem and then its solution, rather than being the basic creator of the problem. We think that the data, as I said earlier, is going to tell us some things about where we need to go in terms of thinking about how to manage the industry effectively in the future. Just a word on the restructuring here very briefly, just bring everybody up to date on it, get everybody playing on the same page. Since 1987, the restructuring created 7 Class I railroads. The carriers during that time, for a variety of reasons, not just the restructuring, but because the business structure that they've had to deal with has changed, of safety necessity of reshaping themselves, not a lot of factors like their physical plants, their operations, the way they manage their networks. They've had the opportunity to take advantage of some economies of density and scale that were not available earlier. The size of the current carriers changes the whole game in the way you can manage the network. If you're doing research into this and you're doing some investigation of it, it is a wonderfully rich period of data, and because it's like you never want to waste a good recession for data because it gives you data points you wouldn't otherwise have in economics. This stuff is the same thing. A good crisis like this creates data that you would not otherwise see out there and would not otherwise be available. So, starting to look at network performance. If you look at it out there today, it's based on 2 factors. And the first one is really the traditional factor in which railroad management stood. This was the lever they pulled when they wanted to change things. Physical assets to the human assets. That's what you managed largely in railroad paths. The thing, however, that is emerging as being the critical item to manage are these processes through which the assets are deployed. How are you managing these assets? And it's what's become very clear and what stands out in a lot of the information that you see here is that this process issue is becoming more and more the important more and more important managing large, complex networks, much more so than it had been in the past. There was a point in the past in which you could look at it at the network out there, and you could manage it based on intuition and experience. In many cases, that's past, and you're to the point where you need the process, you need the planning, you need the thinking. Quite frankly, you need a lot of the things that I saw going on here yesterday. Develop more as the industry develops more effectively. Two basic definitions before we dive down into the data and talk about that a little. The measure that we use for network performance is network velocity. I'll show you that in just a minute on what that looked like during this period. It's a basic measure of how the network performs. It's measured in miles per hour, and it includes all the time that trains spend on line of road divided by the distance that they go. All the time, including the time stopped. Has nothing to do with how fast they're running. You find that the big thing that has an impact on network velocity is not how fast you run, but whether you're moving at all. Zero is the bottom of this. Chris.
I'll shout it so the mic can hear us. But just to be clear, it does not include time in terminals.
No.
It's from the point of departure of a terminal.
It is the time on the road of the trains from the time they depart the terminal until they arrive at the following terminal. But does not include time in terminals, but does include all the kinds of delay that you can get out on the road. Meeting, passing other trains, bad order equipment, weather, you name it. If there's a potential cause of delay, that gets rolled into the network velocity number. The other one that we're going to use in here is track speed. And for the purposes that we have in here, that's the speed reflecting the minimum time over which trains can transit a track segment. Okay. Track speed, by definition, always has to be larger than network velocity. And in fact, it should, in a healthy network, network velocity should never be less than 1/2 of track speed. I'll explain that a little bit later. But that's kind of a basic relationship that if it starts getting anywhere less than 1/2 of track speed, you've got serious problems in the network. So during this period, this is what happened on network velocity. And what you can see over here is that you were getting an increase between 1987 and 1992. Then it started falling. And it hit rock bottom here for the first time about 1997. But the critical thing about that period is it started falling, and it started falling rapidly long before the major consolidation started taking place. And that's one of the things that leads you to the conclusion that there had to be something else going on in here besides the impact of the consolidations and the problems that were there in putting the networks together. Is that you got this decrease here. Fell down here through 1997, actually improved a little up through early in the first decade of this century, up to about 2001. Then fell again to a new low by about 2005, and since then is seen dramatic improvement. It's amazing what happens when a lot of business goes away. But the important thing is that the improvement has started here, and the peaks for the business were later on here, which meant that again there was something going on out there besides just the obvious. Again, it was when we first plotted this chart that it said it's time to question the traditional look at what happened to the rail network back in the mid to late 90s and the early part of this century. It's something very different happened from what we traditionally think about. decided to look at 4 things that we could measure. Now, quite frankly, it's kind of constrained by what you can measure. Average track speed, slow orders within the network, impact of increasing train density, and then terminal fluidity and operating capacity. And again, keep in mind that we wanted to do things that we could measure out of publicly available data. Now, because if you look back at this chart again, most of the really interesting things occurred between there and there. That's where we'll go ahead and focus most of the rest of the conversation is that period between 1992 and 2006. So looking first at average track speed, 1992 it was 41.4 miles an hour. 2006 it was up to almost 45 miles an hour. Okay, during this was a time when you'd had a dramatic drop in network velocity, 5.3 miles an hour drop in network velocity, but at the same time, track speed was actually climbing. Actually, mainline track speed was climbing during this time, based on upgrades, based on the fact that during this time the densities were increasing and a lot of lines that were becoming main lines were getting upgrades, getting signal systems added to them. A lot of things happened during this period that drove that increase in track speed. But clearly, if you have track speed itself increasing, it's probably an unlikely source for a decline in the overall network velocity. And so it's probably not where you want to go first when you're looking at the potential for decline in network velocity. Slow orders. Well, this is something a little bit different. If you look at the slow orders on main track, slow orders being where you are having to operate on the track below the authorized track speed, it increased from 1.7% on a 92,000 mile network to 4.5% on a 99,000 mile network during the same period. Okay, so that's something that's worth looking at as a potential cause of some of these problems. What was causing the slow orders? Well, a couple of things. One was the capital expenditures that were going into the network for dealing with capacity increase requirements, and two, if you look during this period, there was the absorption of several smaller class 1s into larger ones that had a lot more money to put into maintenance. And so there was a lot of maintenance upgrades that were going on some of the class 1s that had been capital starved in the past. But if you look at what happened on slow orders, we looked at a methodology of saying, okay, you have to deal with averages in this because you're dealing with system-wide data. What was the average impact that you get from slow orders on the network during this time? Well, you use the basic data in there is average track speed, distance traveled, and average train length, with some estimates on the impact of slow order length and slow order, the delay that you get in it. But if you throw it all together, you only get impact on this on a network-wide basis of about 0.3 of a mile per hour from the impact of slow orders. Okay, so yeah, is it a problem? Yeah, it's driven down network velocity, but it doesn't. Even if we were wrong by 100% on what we estimated the slow orders to be, and what we estimated the impacts of each slow order to be, you're still not explaining 5.3 miles per hour of decline in velocity on the network. So it's clear that you need to take a few more steps here. And these are just talking about what some of those data points were that we had before in terms of average distance operated per train start, the mainline and branch line average track speeds, and average lengths of trains during this period. So again, a lot of this is not direct data that is in the R1 reports, but is data which you can take out of the R1 reports with a little thought about what is actually in there and what it can tell you. The computational process, and quite frankly, if there's anybody that has an interest in it, we have a computational appendix to the report we did for TTCI that we can explain in detail all the computational things that went on here. So, slow orders alone, clearly a source of disruption, but you can't account for what took place between 1992 and 2006. It seems that the slow orders tended to have been offset pretty much by the increase in average track speed during the same period. So again, it was there's a number of moving parts here, but this one does not by itself seem to explain what was going on. Increasing train density, probably a much more likely candidate. And if you look at the network, it's clear that the train density, the number of trains that you were operating out there were increasing, both in terms of the tons and the number of train miles that were increasing. In terms of ton miles, I put it up there that, in 1992, you only had 52,000 miles of the network that had about 20 million gross ton miles per year, gross ton miles per mile per year. Whereas in 2006, that had grown to about 70,000 gross ton miles per year. Now, at the same time, you had 67 billion of capital spent on infrastructure during the same period. So you know that there's going to be some offsets in that. The other thing that happened during this time is a lot of that 67.5 billion went into additional track and sidings. One of the things we know here is that there were over 1,800 miles of additional second and third main track that were installed in the network during this same time period. So we get using the same kind of approach. We looked at how many, if you had this much additional traffic on the network, what was the increase in the probable number of additional delays that were due to meeting additional trains that would be out there? So we had to first of all construct a way to compute what the likely number of trains per segment were in the first period and how they changed over time. Again, for those of you that really need something to put you to sleep at night, we have the computational process in there. But the net effect was that average track speed with the 1992 density would have been taken down. Remember, it was 41.4 miles per hour in 1992. Was the track speed without any delays. Due to density, it would have been taken down to 38.33 miles an hour. So it would have decreased, as you would expect. Average track speed in 2006, though, actually was at 39.68. So you had the average track speed and the average unimpeded track speed, less that was with density. I'm sorry, it's one of the typos that I didn't find in the slide. Should be density there. It allowed it to go up because you had an increase in track speed. The additional density, although it takes more time to get across the track, actually, after you figure it all out, the average track speed, if it was just due to density, goes up a little bit here, up 1.35 miles an hour. which you would say, okay, then this is not explanatory at all, but if you go to what we have in here, it is a potential source of disruption, but it appears that, at least in this case, the capital spending kept up with new track capacity. Now, what happens if you throw the slow orders and the track capacity together? If you do that, it changes the answer a bit, because you get a reinforcement of the effects of it, but you go through the same type of analysis, and you start to get a significantly slower slowing of the network, the 1.41 mile per hour. But that still explains only about 27% of the total reduction in the change in network velocity. And a part of this is because the real capital expenditures during that time, again, were kind of keeping up with what was going on in the network, in the broader network. But it becomes useful to look at what would have happened if you had tried to impose the density of 1992, or rather the density of 2006 on the network as it was in 1992, with the performance that it was getting in 1992. Quite frankly, without the capital expenditures, you have a disaster on your hands. And that was one of the results we get out of this, is that without the capital expenditures, that if you tried to do the density of 2006, you had over a 7.5 mile per hour decrease in network velocity that would have resulted from this process, which is 2.27 miles per hour beyond what actually happened. So regardless of the effects we're going to talk about here in just a minute, you would have had, my guess is that this plus the additional effects that would have come from other sources because of this, if you had not had that capital expenditure, you'd have had well over a 10 mile per hour decrease in network velocity, which would have been approaching 50% of the network velocity in 1992. Would have disappeared, again, without the capital. Okay, so what is it then that can drive velocity down? It is the things that drive train speeds down to zero for extended periods. That's really what can be the big driver. It can't be done, quite frankly, using line or road factors only. Even with the increases in density, it's going to be difficult to do. Maximum impact from line or road factors should be no more than the absolute maximum of about 50% of the unimpeded track speed. Why? Because even if you run one direction only one direction is operating, that direction, if the other direction is stopped completely, should be operating at track speed. So if you can, at the very worst, you can fleet trains through the network at approximately 50% of track speed, less something like slow orders or something, things of this nature. You can, that's about the worst it can get, is the track is 50% plus slow orders for the network, unless you're driving train speed to zero out there because of some other factor. The other factor for those of us that have lived through this, and some of us started living through it when I worked for Southern Pacific. You lived through it a long time before you saw things like this happening from the mergers and consolidations. The other factor that if you've done that, you know it starts in the terminals. The the congestion issues, that's where they always start, because that is what drives train velocity on line of road to zero, is terminals that can't accept delivery of trains. That's almost inevitably the starting place for bad problems with congestion. Quite frankly, train, usually when a train doesn't advance, when it's moving line of road, it's because it has no place to go. That usually means there's blocked sidings, and the most frequent cause of blocked sidings is trains can't get into terminals. Blockage suggests the terminal is usually unable to process cars to get it out the other side. And quite frankly, the trends in if we look at the trends in the industry from 1992 to 2006, it suggests that this is something that needs to be looked at a little bit more aggressively. Now, so we did. We looked at all kinds of measurements for what was happening in terminals during that time. And most of them, if you look at measurements that were built around productivity issues, the performance actually was improving. You look at the cars handled per switch engine hour, the number of cars that were moved through terminals at this time. Almost all the measures of terminal traditional measures of terminal productivity were improving during this time. So it clearly was something else. We finally landed on 4 items that were taking place that we wanted to look at what the interaction of these items were. Total number of freight cars occupying the network, total number of carloads originating each year, the total number of cars moved in non-unit trains, simply because those are the ones most likely to demand substantial handling in terminals and require resources there. And then the miles of yard and switching track available to support the work in the terminals. And these are where the measurements were going. The first one up there, active freight cars. We had that number of active freight cars in the system was increasing most of the period. There was a drop there right after 1999, but it didn't peak until about 2007. So clearly, the number of freight cars in the system is increasing. Why is this important? Well, the increase that you had in freight cars there generates a need for track space with that number of freight cars of increase of about 2,150 miles of track, just that those cars will occupy. And if you look at what happened in 1992, there were about 12,000 miles of freight cars running around on the U.S. network. By 2006, this has gone up to over 14,000 miles. There's your 2,150 miles of additional freight cars that were out there. Most of the time when these things, whether these are being stored or moved or whatever is happening, most of the time that occurs in yards. So you had an additional need for track space on the network just to handle these additional freight cars of an additional 2,150 miles. Not likely to be on main line. Okay, the non-unit train carloads originated, again increasing. The total increased steadily 1992 to 2006, and then the total carloads grew during that period. The non-unit train carloads grew. 1993 to 2005, you still had an increasing demand for terminal services out of the network during this entire period. And then finally, the amount of yard switching track that was available for the whole thing. 32,000 miles in 92, 26,000 miles in 2006. And then, quite frankly, you didn't really have this 26,000 miles. You had to really adjust it downward again for another 2,000 miles because of all those additional freight cars that were out there. So the amount of track that was available to actually switch cars in terminals dropped to about just a little over 24,000 miles from 32,000. So by roughly 25% during that period. Finally, if you put all the trends together, make an index out of them, this is kind of what the world looked like during that time. Basically, demand going up, supply going down. Now, the next thing you needed to look at was, with all those cars that were increasing in the network, the handling events that took place. And this turned out to be the most challenging thing we had to construct coming out of this whole thing. Because there are two types of events that we had to handle, had to develop, and that was an estimate of intertrain events and one of the origin and destination events. Intertrain events, we could, based upon the average length of train movement plus the average length of haul, we could come up with numbers on that. Origin and destination events, we that you obviously have one on each end for these cars, but in addition, you also have something related to the movement of the empties for everything. So for every loaded event, there's a loaded and some portion of an empty movement going on. We know that even with the inclusion of the empty material, this almost certainly, what we have to do almost certainly understates the number of actual events that happen, for the simple reason that we couldn't find things like reciprocal switching events, handling of events for cars going to bad order, rehandling of cars that has to take place in yards on a regular basis. Bottom line is that on this one, it's kind of to do the best you can with the data available, knowing that it's probably understating the impact. But if you look at it, this was the events per loaded non-unit car that unit train car that took place during this time. Started at about 10 events over there in 1987, went up to, by 1993, it had gone up to about 12 events per car, and has gradually dropped back to around 8.5, which is where it is in 2009. I think when we updated it for 2011 data, it was still pretty close to that 8.5 events out there. So it's kind of reached a plateau for us. And again, this is pretty much what we were just looking at. What happened in the yards? That what it strongly suggests is that if you look at the timing on some of these things, that as traffic was increasing here, yards were becoming increasingly congested during that period of time. In 1995, you started basically the first of the large mergers and consolidations that took place. And then after that, other than this one or two blips in here, much small, most of them relatively small, you get almost a continuous downward trend in the number of events that it took place to handle a car through the network. And what this suggests, given the timing on it, is that as these large systems were put together, that you were starting to get the ability to move cars through the network for longer distances with less handling, and that you did not need the amount of handling that had been taking place in the past as you got further out into the implementation of some of the consolidations. What were the factors in this that kind of drove this? Well, there were fewer required interchanges. Interchanging freight on railroads, between railroads, is just a very convoluted event. Often, while there were greater origin destination volumes, there was an ability to handle things through the network long distances without switching, and you saw the increase in the operation of interline trains, which eliminated interchange events, even where interchange had to take place. And what happens over at St. Louis today is a classic example of this. If you look back before the consolidations, you had lots and lots of business going into St. Louis, having to be switched there, handled again, switched again, and then moved out for connecting carriers to the east or to the west. Today, most of that interchange takes place in a little town south of here. The actual interchange location, I think, is Salem, Illinois, and the physical interchange where the trains actually change hands is north of there in various places. The largest one being St. Elmo, Illinois. So, and these trains run through. They don't require doing the physical interchange handling that was there in the past. And that's happened not just here, but all over the industry during this time. So, by looking at the switching events per mile of available yard track, and then adjusting those values for the additional freight cars in the system, and putting all this into an index, you can start to look at the relationship between the handlings and the volume of the network. Because it turns out to be an interesting relationship. As the handlings go up here, handlings per yard track go up with the volume of business, you see that's when the deterioration of the network velocity takes place. As the handlings go down, that's also when the serious improvements start. So between the increase here, which is the handlings per yard mile, and which is the volume increase, even though the handlings per car were coming down, the volume increase was more than making up for it. It was taking you up quickly there through 2003 roughly. And it was only after about 2003 when you started to see the full implementation of the new operating plans that came out of the consolidations that you started to see the handlings per car drop down, even in the face of volume increases as they were taking place beyond that point. And as I noted, the relationship between the two is pretty strong. It's unusual with this kind of data to get a correlation coefficient over 0.8. And this one, whether you adjust it, which is what you have up here at 0.83, or don't adjust it up here at 0.83, or adjust it, which you do down there with the 0.86 correlation coefficient, those are extraordinarily high numbers for this type of data. Suggests that what we already know, that the data bears out the fact that you cannot separate terminal performance and line of road performance, and that terminal performance may be the critical issue, particularly if you have basic tools in place for moving things over the line of road. If you don't have the terminal performance and the plans which match the size of terminal performance to the available resources, you're going to have a problem with the way your network performs. Implications on it are just what we were talking about. That improvements in terminal performance, reduction in switching, have not come from increasing the size of the terminals. They've come from the plans that have been implemented. I think that's an important lesson that we were able to take out of this. In fact, I would argue that generalized terminal growth would not have been productive. Diverted resources away that you needed for the line of road capital. It would have diverted resources away that you needed for new terminals that were replacing, in large part, some of the existing infrastructure. It would have increased maintenance costs, and it would quickly have become obsolete as the plans went into actually took hold and started improving the performance without the expenditure of capital, which kind of gets you to what to why railroads think of capital the way they do. That they've learned to think of capital as the first thing that before you spend money on capital improvements, is there a process that will allow you to improve utilization of your network? Secondly, is there information systems? Are there improvements there that will help you improve the performance of the network? Third, before you put iron in the ground, is there any way that you can use what I call mobile capital, equipment and human capital to improve the performance? And then finally, putting iron in the ground. And this is one of those cases where it became evident that it really would have been the wrong thing to do, to put physical resources into the terminals, given the potential results that would have come from those resources. Implications on this: huge role that's been played by the operations planning in the management of the large complex rail networks. That this has emerged as such a key important item during this time for the management of rail networks. And again, it's one of those things that makes some of the work that I've seen here as important as it is. The critical relationship between terminal fluidity, capacity, performance, including line of road performance. But you can't have line of road performance without dealing with terminal fluidity. And the other implication on this is any kind of policy change which increases requirements for switching is almost certain to have a negative impact on performance of the network and for customers of the railroad. And to this, I get to things such as we're seeing in front of the Surface Transportation Board today, such as the proposals for universal forced access switching. I'm sure that there are a lot of customers that think that are great. The question is whether those same customers have thought through the consequences of doing that in terms of what the impact can be on the rail network. Conclusions of this whole thing. Certainly the density and the slow orders were important. They would have been far more important for deteriorating the network performance if we hadn't seen the capital infusion that happened during that period, and in fact is still going on. But as it was, they can't explain everything that happened between 92 and 96. Data indicate that in the absence of serious line of road congestion problems there, best indicator of network velocity is going to be those switching events per yard track, mile of yard track that's available to perform those events. And that it's going to be a pretty strong indicator of what's going to happen in your network as long as you have relatively good performance out of line of road, or potential performance on line of road. The solutions to the yard constraints don't necessarily involve construction of additional track. It's more about operating planning and blocking strategies that are critical for relief of yard congestion. And also, as we mentioned before, it looks like the investment in line of road between 92 and 2006 did keep up with the growing business demands for line of road. It took a while for the planning to take advantage of all the opportunities that were out there and deal with what needed to happen in the terminals. The other thing is that I would argue from everything I've seen in this and from what what is, comes through all the data that I've come across, not just what's in here, but that the consolidations really uniquely position the rail industry to deal with the terminal volumes congestion through something other than through plan redesign rather than capital expenditures. They uniquely position the industry not just to do that, but to deal with business expansion opportunities in the future through some of these same mechanisms, and allowed a much more judicious use of capital and the way capital is employed in the industry. And with that, any questions?
We definitely have time for some questions. So.
Yes.
I have two sort of related questions. One is, to what extent do you believe, I mean, you're looking at aggregate numbers here, to what extent do you believe that these trends that you saw in the network as a whole were also indicative of component railroads? And were there railroads that, for example, were slower to adopt changes in switching strategy, were slower to take up their yard track, weren't doing as much capital investment? To what extent is this aggregate snapshot also a useful indication of what was going on within each individual railroad? And then to follow up, what feedback have you gotten from railroad operators to say, oh yeah, you're right, that's what was happening on our railroad?
Dealing with the first one, the difference between the aggregate trends and much more disaggregate, much more granular look at the network. One of the slides earlier on said that there were problems all over the network. They were at different times. They were at different places. These problems moved around. So if you look at the network for what happened during the Union Pacific Southern Pacific merger, clearly the center of the problem on that was on the railroad involved. But there were impacts on that for a lot of other railroads, and with because things were delayed for them, it made the planning, it made the scheduling, it made the handling much more difficult for other railroads. And I know that's the case because when you had the problems with the disassembly of Conrail in the east, it created similar problems. You could feel it in the west. Because these things do operate as a network, none of these problems tend to be isolated to one carrier. Yeah, they may be more intense in one place or the other, but everybody gets to play. I mean, there's no exclusivity on this deal. So that's a big part of this whole thing is that, like I say, you could take the same data, you could drill down and say, okay, what happened on this particular railroad at this time? You use the same computation series and go through it. I'm not, it tells you something, but I'm not sure that it tells you an awful lot, because you're kidding yourself if you think it's isolated there. Okay? And I don't think the data is robust enough to say that, okay, we can isolate it on this railroad, and because this one didn't change quite the same way, that's really the difference in impact. I don't think the data is quite that robust. So, in fact, I know it's not. So I'm hesitant to do something like that. The second thing, feedback on this. Well, if you look at it, conceptually, what we've done in the presentation that we've made to the STB on Ex parte 711 and the proposals for forced access switching are based around the same concepts. We haven't used the same data here. We've gone into different data. We've explained it differently, but we started out by looking through this material here and then say, okay, how do we repackage it so we can put it in front of the regulatory agency? And it's very much the same concept, is that switching is bad. Yeah, the switching is, it's necessary, but it is easy for it to become what can create your network, make it non-functional.
Thank you.
Yes.
Could you talk a little bit more about how consolidation will be a causal event to reduce the number of handlings? I mean, it's sort of intuitive how you mentioned that runs might be longer and you got to run through trains, but what else makes consolidation reduce handling?
A big thing is the density that it can create. If you have the consolidation, you also inevitably come up with more traffic that is matching origin destination pairs for longer distances. And when this happens, okay, instead of running a half train and switching it at a terminal further into the network, you run one full train, okay, and so you don't have as much intertrain switching when you do that. You can bypass major intermediate yards is the big thing on that. And it's the same thing on network flows. You'll find network flows now that are running between carriers that are running across boundaries. I know that in North Little Rock, we blocked trains for CSX and to move to Selkirk, for instance. But you'd run an entire Selkirk, New York train out of North Little Rock, or you'd run a Willard, Ohio train, or you'd run an Elkhart train, or for CN there was a Toronto train. Things like this suddenly become doable because you consolidate volumes. You can consolidate volumes and put them in one place, and that's the key to is taking advantage of the densities that are created in the network. Anyone else?
I'll stand by the mic, save Tim from running across the room. So one of the things that I remember during the mid-90s, when some of that slowdown started to occur, was that ironically, car orders went up because cycle times were increasing, so a shipper needed more cars to accomplish the same volume of transportation. And so we were pouring cars into this increasingly congested network. Mm-hmm. Did you try to look at that particular factor at all, or?
Well, that's the key factor of what happened with that 2,000-mile increase in the number of cars there, was that and that if you look back at the correlation coefficient between network velocity and the number of switches that went on was 0.86 for if you looked at those additional cars and the additional impact that they had. It was only 0.83 without it. So clearly they were a factor that was improved, that was bringing it closer. Beyond that, quite frankly, the data is not robust enough to get far beyond that. Again, and that gets back to the question earlier about how do we use this going forward with for various reasons. That's one of the reasons we had to repackage these things for the STB into something more focused. Is because when you're looking at very gross data like that, you can get trends, you can get ideas of what's going on, but you've got to draw out something more precise if you're going to be convincing in the arguments. Yes.
We can bring the mic over.
think you indicated that you had much better results in performance as a result of planning than you did by the increase in physical planning.
Yeah.
Do you see us getting to a point where we have reached a saturation point on that, where we have no choice but to increase physical plant soon?
Oh, yeah. Oh, yeah. There's no doubt. There's no doubt that you know, that's like anything. You can only carry the trend so far. I don't think that the planning is a replacement for the physical, the work on the physical plant and the additions to infrastructure. I do think it is a way that you can much more efficiently focus those investments, so that you're able to focus them on the parts of the network that really need the investment today and are going to need it and be able to use it long term into the future. And the planning gives you options on that, and it gives you important options given the constraints that we have on capital. You know, yeah, there's just so much capital that you can put out there. The planning doesn't solve all the problems. Eventually, you got to have something. You know, it's like Rob Krebs when he was at BNSF used to say, talking about some of the problems with network management. He said, you know, we're different from the rest of the world. Electrons don't eat, and you can move them around and all that, and you can think about it. But eventually, you've got to have that physical asset. You know, that's the bottom line. But planning creates options. It says that in this case, it said that if you think through where you really need this money was in line the road, you were getting dramatic increases that you could afford to put off the investment in the yards because there was a way out of that problem eventually. And so it gave you the option to focus the capital where it was really necessary for the long term.
First of all, before I ask, were there any other questions back here? I didn't mean to insert the mic. Okay, I'll give it back. So I have two questions. One is, and I apologize if I missed it in your presentation, but was part of your study to actually somehow quantify the units of additional capacity, essentially miles of double track or something like that, or was it more at the level of just dollars of investment?
Actually, the ultimate purpose on it was to look at some of the physical impacts that were resulted from what the performance in the network was versus what it might have been if it had been a free-flowing network. In other words, what was the physical and ultimately translatable into monetary impact of having all that congestion in the network? And yeah, there were big impacts. You saw one of the things we plotted was what happened on fuel trends, and during this period they just dropped down dramatically, and eventually went back up to where it meshed with the trend going forward. But you had a hole in the trend that went down there during this period. In train performance, and you know the number of crews that you needed, the number of train miles you had to operate for various things. Again, you got a hole in that performance that was very detectable. It was we were surprised that that it would be as detectable as it would be. So that as I say, I'd have thrown that in, but we'd have been here for another hour and a half. So.
All
So the switching events per yard mile metric, which seems to be a pretty key one, I'm gonna assume that's just manifest, non-unit, non-intermodal.
As much as we were able we know it's non-unit, but when you look at the data in the R1, it's clear that unit trains in there is much more than what we think of as unit trains. It's clear that there are also some things like intermodal trains that are thrown into the unit train calculation. So as much as we could isolate it on the manifest business, we did. That's what we were trying to get to.
So anyway, what that leads me to wonder about is intermodal, and it's obviously much more sensitive to network velocity than the marketplace. And so I think a lot about the new CSX terminal in Baltimore. That's essentially a classification yard for containers. And
Exactly.
they're handling those too. Yet it feels like that hub and spoke kind of concept is maybe going to be a positive thing as an innovation. I don't think we know yet, but can you talk a little bit about that and how handlings might affect intermodal traffic?
Well, if you look at the CSX one in Ohio is a prime example of this, but there are some other terminals around the country that have been built with this same concept in mind. And if you look at the way those terminals can be used, it can be exactly as you're saying, almost as a classification yard for intermodal freight and transferring loads so that you don't have to switch rail cars. That's because switching rail cars, whether it's in intermodal service or in manifest service, takes a lot of track, takes a lot of time, takes a lot of expense. It can be much easier to handle things at the box level. And so, I think that what you see is that yes, that is a hub and spoke type operation that's been created. Essentially, that's what a classification yard is a hub and spoke type thing. Comes in on some trains, goes out on particularly a large one will go out on a lot of different trains. But you have a choice in the intermodal business. You can actually do that same kind of switching, and I think that's being tried in a couple of places too, where you actually switch the rail cars. And so, which one is better? I suspect that it depends upon the particular volumes and the number of interactions that you have. That where you have a relatively small number of interactions, it's probably better to spend the money on a little extra track and create something where you physically switch the rail cars. If you have more than that, it may very well be that you want to move the containers and not the rail cars.
So you're talking about blocking strategies for intermodal.
Yeah, you really are. They've always been there. We're just as the technology matures a little bit, we start to learn to use it better. With that.